Hey, it's my pleasure to introduce Udolf Fauder from University of Warsaw, who'll speak to us today about strong G2 structures with torsion. So please, Udolf.
Oh, thanks for the intro, Jeff. Okay, so today I will talk about strong G2 structures with torsion. And most of the things that I will say in this talk is based on this joint work with Anna Fino at Turin. And most of the content of the results, you can find it in this paper, which is on arXiv, and it is now published as well. So you can find the published version. The results is the same. Maybe it has a bit more details, but that's the only difference. Okay, so in this sort of series of talks, we've heard about the strong Kähler manifolds with torsion, strong hyperkähler manifolds with torsion. So this talk is going to be about the G2 version of these talks, and I will try to sort of make some analogies with the different type of A structures and what sort of results, what sort of similarities can be made to hold between these different cases. Okay, so the plan of the talk is first to give you some sort of context and motivation for the whole setup. This is probably going to be boring for most of the people in the audience because you've heard it over and over again. But in case I have to make the talk sort of a bit self-contained, so I'll try to cover some background and motivation. Then I'll discuss the main part of the talk, which will be the SU3 and the G2 cases. And then towards the end of the talk, I will talk about possible geometric flow approach to studying these strong G2 structures with torsion. Okay, so let me start. So the setup is as follows. So you would like to study a Riemannian manifold, MG, with a metric connection. So you have some sort of differential operator, and you would like it to be compatible with your underlying structure. So it has to be a metric connection. And the thing is that if this is the only property you ask of your metric connection, then there's infinitely many such connections. So any metric connection is determined, can be sort of determined by a one form that values in the Lie algebra that preserves the metric, which is the space of two forms. And metric connections are completely determined by the torsion. So the torsion is the tensor T, which is the tensor that eats two vectors. It's Q-symmetric in X and Y and spit out a vector. Now, because I have a metric, I can sort of just lower the index to get one form. So I'm going to think of the tensor as the torsion, as a two form that values in the space of one forms. Now, as an ON module, this space is reducible and it has three irreducible components, a one form bit, a free form bit, and something which is neither a one form and a free form, and I'm going to call it T21. So typically, this is called twistorial type, the space of tensors. It's called twistorial just because of a name that I found in a paper by André Moriano and Michaela Pilka. Okay, so it has nothing to do with twistor theory, so I should mention this. Okay, so the way you get the one form bit out of this two form tensor one form is simply you contract the one form inside the two form to get this one form bit. And because one forms are isomorphic to vectors, you will call, if the torsion lies in the space of one forms, you just call it's of vectorial type. If it's totally skew-symmetric in the two form and the one form bit, so then you get the free form bit. And if the torsion lives in the space, then you call it a connection with torsion of skew type. And if it lives in the last bit, you call it a connection whose torsion is of twistorial type. Okay, so some basic facts about metric connection is that the fundamental theorem of Riemannian geometry tells us that there's a unique connection which preserves the metric and is torsion-free. This is a left-shift connection. And this connection with skew-symmetric torsion turns out to be, you can characterize them as connections whose geodesics are in fact the same one as the left shifter one. So if you're interested in sort of studying Riemannian geometry from the point of view of geodesic, there's no preference as taking the left shifter connection over another of these connections which have skew-symmetric torsion. Just from a sort of a PD point of view, why would you care? So today we will talk about these connections with skew-symmetric type torsion, but just from a PD point of view, why should you care about the case when the connection has torsion of skew type instead of vectorial type or of twistorial type? The point being that if you would like the connection to have torsion of vectorial type, that means you will need the components of the torsion in the other two spaces to be zero. And that's a lot of PD because both of the spaces is a lot of constraint. This behaves like sort of n cube over 6. This behaves like n cube over 3. So this is a lot of PDs that you have to impose. So connections with torsion of vectorial type is usually very constrained. On the other hand, if you're interested at looking at connections whose torsions of twistorial type, then you will have to impose that the other conditions here vanish. But this is typically an underdetermined system. So typically in practice, there are infinitely many connections which are of twistorial type. So there's no canonical type connection in this sort of problems. Whereas the skew type turns out to be sort of the sweet spot where they sort of, it has enough sort of freedom, but at the same time, it's not too constrained. Okay, so the problem we'd like to study is that of manifolds which admit connections with skew-symmetric torsion and with reduced holonomy inside ON. And the motivation for doing this is because they arise very naturally in several problems. So for instance, they occur in the study of the so-called Hull-Schrödinger system in the context of heterotic string theory. They are very important in the context of complex non-Kähler geometry, because when you have a complex manifold which is not Kähler, typically using the Lev-Shifter connection is not a good idea because it doesn't preserve the underlying complex structure. So it was sort of Bismuth who realized that you can find, in fact, another connection which actually preserves the underlying structure, and it has skew-symmetric torsion. And this is what is typically called the Bismuth connection. And also, these connections with skew-symmetric torsion plays an important role in the context of generalized geometry and generalized ridge flow. Okay, so if you want more details, you can look at the other talks in the seminars. Okay, and so today we'll be interested in the case of strong H structures. So what is a strong H structure? So for me, a strong H structure would be a connection H, a connection nabla with skew-symmetric torsion T, such that the holonomy group of this connection lies inside some subgroup H, and it has closed torsion. Okay, and this is what I'm going to call a strong H structure. And what we would like to do, we would like to be able to understand the geometry of such objects and hopefully try to classify these objects. So note that in contrast to the torsion-free case, so when the torsion vanishes, we have Berger's classification of possible holonomic groups. In principle, for the Lev-Shifter connection, in principle, for connections of skew type, as far as I know, there's no classification of possible holonomic group. That's why you have to impose typically that the holonomic group lives in a certain subgroup. Okay. And the main reason why this happens is because these connections typically do not satisfy the Bianchi identity. Okay, any questions or comments? Okay, good. So let me start with the first setup. So first, I'm going to look at almost Hermitian manifold with skew-symmetric torsion. So let P denote my almost Hermitian manifold with metric G, almost complex structure J, and the Kähler form would be denoted here by omega. Notice that I only assume that the manifold here is almost Hermitian. I will not impose that the almost complex structure is interbal or anything. So the first question one should ask is, does there exist a Hermitian connection with skew-symmetric torsion? And the answer to this question is yes, but typically it's not always yes. There's typically an obstruction to this. So the answer to this question was given by Friedrich and Ivanov. That says that a manifold admits a Hermitian connection with skew-symmetric torsion if and only if the Ninhuys tensor is of skew type. So remember, the Ninhuys tensor is this tensor defined by this object here, and it is a tensor that eats two vectors and spit out a vector. But because I have a metric, I can always sort of lower the index, so I can think of this as a two form that values in one form. Okay, just like the torsion does. And again, just like the space of torsions, this has three components. This splits into three irreducible components, and I can look at the Ninhuys tensors component in each of them. And the theorem says that there exists this Hermitian connection with skew-symmetric torsion if and only if this Ninhuys tensor lives here. Okay. And I will call this connection the Bismuth connection. Bismuth sort of introduced this in the case of complex manifold, which is automatically in this case, the obstruction vanishes automatically because for complex manifold, the Ninhuys tensor is 0. So typically, one just defines a Bismuth connection as a Hermitian connection whose torsion is given by this guy here. So in general, for the almost Hermitian case, you have to factor into account the Ninhuys tensor. Okay. So yeah, so one sort of comment I should say is that here I am writing dc of omega to mean j of d omega, which is probably not standard because some people typically put a minus sign just to sort of fix my convention. Okay, so now let me sort of specialize to the SU3 situation. So from now on, I'm going to assume that the underlying manifold has dimension 6, and I'm going to assume that it has an SU3 structure, meaning that its canonical bundle is trivial. And so I can pick a section of this of constant length, and I'm going to denote this section here by capital omega. So this is a complex free zero form, so it has a real and an imaginary part. So I'm going to denote this by omega plus and omega minus. And the data of this metric, this almost complex structure, the two form and this complex free zero form is going to be called an SU3 structure. So typically when you have an SU3 structure, it's typically not iterable in the sense that the intrinsic torsion doesn't vanish. So let me say what I have just on the slide right now. So if you ignore everything on the right-hand side, if you ignore this for the time being, if d omega and d of capital omega plus and minus were to vanish, then this manifold would be Calabi-Yau. So it would be a Calabi-Yau prefold that would be equivalent to sort of saying that its two form and this holomorphic free zero form are parallel with respect to the Lev-Shifter connection. So the failure of this being true is measured by a certain tensors, and this is known as intrinsic torsion. And this is what is precisely written here on the right-hand side. So the tensor, the way I've defined this tensor pi's and sigma is so that the index, the subscript, tells you the type of tensor it is. So pi0 here is a zero form, so it's a function. Pi1 is a one form, pi2 is a two form, and this new free is a free form. Okay, and this is what the intrinsic torsion is. So there's two quantities which will play an important role for us. The first one is the Lie form, which is this one form here. So you can define it up to a constant factor as j of the codifferential of omega. And the second thing I need to tell you is that in fact the Ninhais tensor is actually fully encoded into this intrinsic torsion, and in fact it is determined by this pi0 sigma 0 and this pi2 and sigma 2. Okay, and it turns out that if you compute what the Ninhais tensor is, it's given by this expression here, where pi0 and sigma 0 are function, and you multiply them by this complex free zero form. So this is a free form. So this guy here clearly lives into lambda free, and it turns out that there's an isomorphism that maps these two forms, which are of type 2.8, inside these tensors, which are of twistorial type. Okay. So the point here being that for there to exist a bismuth connection, you will need these two terms here to vanish. So you will need this term here to go away. So let's assume this is the case. So if that's the case, then the torsion of the bismuth connection takes this very neat expression. So it's dc of omega times this function times the complex free zero form. Okay. So now before I state the first sort of result, I would like to tell you some terminology. So typically you would call a manifold strong Kähler with torsion if d of the torsion is 0. So if this free form here is closed, you call it Calabi-Yau with torsion, or shortly CYT, if the bismuth-Ricci form is 0. So this is a first representative of the first term clause, and if you want, this is the curvature of the connection that you get by looking at the bismuth connection on the space of free zero forms. Okay, so it is the curvature of that connection. And if both of these conditions hold, i.e. it is strong SKT, it is SKT and it is CYT, then it's called Bismuth-Hermitian-Einstein. Okay, and what I'm going to do, this is typically the terminology one uses in Hermitian geometry, but because in my setup I would like to not consider only the complex case, I would also like to consider the almost Hermitian case with skew symmetric torsion. I'm just going to add the prefix almost to my original definition that we have already seen in previous talks. Okay. So let me now tell you the sort of first result that we found with Anna. So suppose that the Ninhais tensor is skew-symmetric. So suppose that the bismuth connection exists. And let's suppose that d of the torsion and the bismuth 2 form are both J invariant. So they are of type 1,1 and type 2,2 and type 2,2 and type 1,1 respectively. Then the following things are equivalent. The underlying Lie form is parallel with respect to the bismuth connection if and only if the 2 form is in the free form is in fact co-closed, and the Lie form is a holomorphic killing vector field. So what I mean by killing, I mean that this Lie form preserves the underlying metric, and what do I mean by holomorphic is that it preserves the underlying almost complex structure J. So the reason why I use sort of holomorphic in between commas, in inverted commas, is that the manifold is not a priori complex. So there's no complex structure. So when I say holomorphic, it's just in the sense of it preserves this tensor. And it turns out that if you assume that the underlying manifold is in fact almost Bismuth-Hermitian-Einstein, i.e. the free form is closed and the Bismuth-Ricci form vanishes, so the whole group here reduces to SU3, then these two conditions from before is in fact equivalent to asking that the Ricci curvature of the Bismuth connection vanishes. Okay, so the point here is that assuming this if you have a manifold which is almost Bismuth-Hermitian-Einstein and whose Ricci tensor vanishes, then you get an extra symmetry of your underlying space. You have this extra vector field new one that enters the game. So a similar result was sort of previously found by the work of Ivanov and Stranchev. But our proof is a little bit different from what they do. Is in fact we use some results due to, we adapt some results due to Brian. I'm going to talk about that a bit later on in the G2 case. But first, let me tell you some consequences of what happened in this case. So because nabla is a metric connection, that means it preserves the one form. This means that the Lie form has to have constant size. Okay, that's the first consequence of this. And by normalizing the SU3 structure, there's two possibilities that can happen. Either the Lie form is identically 0, so it vanishes completely, or it has constant size 1. Okay, that's the first thing. Secondly, if you play a little bit with the equation, you're going to see that the failure of the manifold to be Kähler is in fact, at least the two form being closed, is given by the norm square of the Lie form and the norm square of the Ninhai tensor. So in particular, you notice that if the manifold were complex, then this term here would die, so the Ninhai tensor would be 0. Then the manifold is Kähler if and only if the Lie form vanishes, because these would be sort of proportional to each other. On the other hand, it can happen that if your manifold is not complex, so the Ninhai tensor is non-zero, then it could a priori be the case that the Lie form could be 0. And then the manifold doesn't have to be Kähler because it is compensated by the presence of the Ninhai tensor. This is a dichotomy that can happen. And you can check from the equation that the scalar curvature of such manifold is always positive. Well, it's non-negative, and it vanishes if and only if the manifold scalar Biot. So in particular, this gives you some obstruction if your manifold is compact. So if your manifold is compact, then in particular, its A hat genus would have to vanish. So this means that there's not every manifold can admit such a structure, for instance. In particular, what you deduce from this is that there are, in fact, no examples on solvable Lie groups, because on any solvable Lie groups with a left invariant metric, the scalar curvature is always negative and 0 if and only if it is flat torus up to cover. So this means that if there are examples on Lie groups, it had to be only on semi-simple. You cannot have any other cases. Okay. So let me give one example. If there's no question, if there's a question, you can just ask at any time. Okay.
Hi,
Okay.
Yuda.
Yes,
Or
Tammy.
can I ask you a question?
Yes.
You said there is no example on solvable, but there are on semi-simple. What about semi-direct product of them? I mean, semi-simple, semi-direct solvable. Could there be?
I mean, if it's completely invariant, then I don't know. I mean, the point here of why it cannot be solvable is just because of the scalar curvature of this condition. In principle, no, I think not. I think not. I think there's a result by no. I think the answer is no, but you have to work a little bit harder. There's this paper by Anna and Lucia and
Alberto.
Yes, they classified all the possible cases in the homogeneous case. In the homogeneous case, they prove that this can never happen. That's what they prove.
Okay.
Yes.
Okay, only of semi-simple. Thanks.
Yeah, no worries. Yeah, cool. Okay, so let me give you one example now. And the basic example is that of the Calabi-Ekman manifold. So you take S3 cross S3, and each S3, I mean, you can think of S3 as by half vibration as a S1 bundle over CP1. And so you can take two copies of S3, and then you can have this sort of product complex structure on the space. Okay. Sorry, not a product complex structure, but sort of mix them. Okay, so then what you can do, you can define an SU3 structure on S3 cross S3 as follows. So let E1 to E3 denote the left invariant one forms on the first S3 factor, and E4 to E5 denotes the left invariant forms on the second factor. Then what you can do, you can define an SU3 structure by this differential form here. And you can check by direct computation that this is complex, so the Ninhai tensor vanishes. The Bismuth-Ricci form also is 0, and the torsion is close. And you can check that the Lie form is parallel, and in fact, the Lie form is given by this expression here. Okay, so this is an example of this strong of this Bismuth-Hermitian-Einstein manifolds. Okay, so typically one would like to classify sub-objects, and we don't quite have a classification yet unless there's some extra condition that hold. So for instance, there's this result due to Apostolov, Barbaro, Lie, and Street that says that if the manifold is Bismuth-Hermitian-Einstein and it is compact, then in fact the Lie form in fact is not in general holomorphic killing, but up to addition of some extra gradient function. And this is not a trivial statement. You cannot actually prove that directly by computation. You have to use the theory of generalized rich flow. So first you have to prove that compact Bismuth-Hermitian-Einstein are in fact steady solitons, and then use the fact that solitons of the generalized rich flow have to be gradient, and then this spits out the function f. Okay, so this is how you prove that there exists a holomorphic killing vector field which satisfies this condition here. So under the assumption that f is constant, so this term here dies off, you can almost prove that up to cover this manifold P has to be either this Calabi-Ekman structures that I told you about before, S3 cross S3, or it has to be sort of Hopf surface cross a copy of C. So, okay. But you need some sort of constraint on the transverse geometry. So this tells you that the Bott-Cohen cohomology is the dimension of the space of 1,1 Bott-Cohen cohomology has to be 2. They have some extra assumption here, okay, which has to do with the transverse geometry of the manifold. So it would be interesting to see, when I don't know the answer to this question, if you can actually drop this assumption. If you drop the conditions that H11B BC is 2, then is it still true that these are the only 2 examples? If so, then this would be a complete classification of compact Bismuth-Hermitian-Einstein manifold with vanishing Ricci, which is not known. Secondly, another question that sort of which is open is, well, what happens if you allow the Nin-Heiss tensor not to be 0? Can you still prove that these are the only 2 examples that exist? The proof certainly would not be, I mean, up till here, everything holds true, but in principle, the rest of the proof uses some complex geometry, which will not be available if you try to prove this. Okay, so we do not know if you can make this result go through in the almost Hermitian setup.
But also, Udolf, I mean, even maybe, I think the question maybe is even open in dimension 4, right? If the Nin-Heiss tensor is...
Yes, yeah, probably you're right. Yes, I don't know. I don't know if one can prove that it is again gonna have to be the Hopf surface. No, I don't know. Yes, probably you're right. Yes, I don't know.
That's true in the integrable case. I mean, which is
yeah. So because it doesn't necessarily have to be complex. That's true. Yes, even the 4-dimensional case that I have no idea. Yeah, it'd be interesting to try to start off low and then try to work in what can happen. But let me sort of say why this sort of strategy might not work in sort of exactly the same way. So let me give you, yes. Oh, okay. So this is an update. So I had to update my slides a few weeks ago. Okay. So recently, so a few months ago, probably it was in January. So for a long time, it was believed that the existence of this holomorphic killing vector field would always have the fact that f would have to be constant. But surprisingly enough, Apostolov and collaborators just a few months ago proved that in fact there exists non-trivial solution where f is not constant. And they prove the examples exist on S1 cross S2 cross S3 and S3 cross S3. So they are on both S3 cross S3 there exist homogeneous examples and also inhomogeneous example, which is quite surprising. This was a bit unexpected. At least to me, it was very unexpected. So okay, so this is one sort of disclaimer here that I should say. So we're not that close to classification result in this case, in general case, as far as I know. So let me give you one more example now. So I'm going to again consider the same manifold as before. I'm going to consider S3 cross S3, but now instead of thinking about it as an elliptic fibration over P1 cross P1, I'm going to think about it as a bundle over S3. And I'm going to embed S3 diagonally inside this to S3. So more precisely, what I will do is I will define a new left invariant coframing on S3 cross S3 by mixing the left invariant one form. So remember E1, E2, E3, E1, E2, E3 was defined on the first factor, and E4, E5, E6 was defined on the second factor. So what I'm going to do is I'm going to define a new coframing by mixing both of these one forms together. And I will define a new SU3 structure on S3 cross S3 again by this new formula here. And you can check by direct calculation that in this case, the Nin-Heist tensor does not vanish, but it is of skew type. Okay, so it's skew symmetric. So it has a bismuth connection. So you can compute the bismuth rich form, it's 0. You can check that the freeform, the torsion freeform, is in fact closed. And in fact, in this case, you can also check that the Lie form in fact vanishes. So what this tells you is that the Lie form doesn't. So what this tells you, if I go back a few slides before, remember I told you there was a potential dichotomy at this point here. The Lie form could either be 0 or non-zero. And if the manifold was complex, this term here would die off. So the Lie form would necessarily have to be non-zero in the complex case. But if the manifold was not complex, it was only sort of almost Hermitian, then it could happen that this guy here would be 0, and this guy here would have to compensate for the failure of the manifold being Kähler. And this indeed does happen. In actual examples, this does happen. So this shows you that if you wanted to just do a dimensional reduction, this is not obviously going to work out directly, at least in the almost Hermitian case. That's how I think about this. Okay, so before someone asks me, Udolf, is this a nearly Kähler structure on S3 cross S3 because it has such a structure? The answer is no, this is not the nearly Kähler structure, because for the nearly Kähler structure, the torsion freeform is in fact parallel, but it is not closed. Okay, so this is a different SU3 structure on S3 cross S3. The complex structure, the almost complex structure is the same, but the metric is not the same. The metric in this case is a bi-invariant one. Okay, that's the sort of difference here. Okay, so any questions before I move to the G2 case? Okay, great. So let me now move to the case of G2 structures. So quick reminder of the basic definitions. So a G2 structure on a 7 manifold is given by a non-degenerate freeform phi, which satisfies this nice property that at every single point there exists some coordinate system where I can write it in this form here. So this is a pointwise statement. This is not a local statement. So at every single point P, there exists some coordinate system. This is a little bit like saying that there exist normal coordinates for a Riemannian metric, which makes it into the Euclidean one. Now, if you're not used to G2 geometry, you might think of how easy it is to find this. Well, it turns out that the existence of such a freeform is equivalent to the first and second Stiefel-Whitney class of your manifold vanishing. So the manifold has to be oriented and spin. So there's lots of examples of G2 structures on 7 manifolds. And because G2 is a subgroup of SO7, this tells you that your G2 freeform defines both a Riemannian metric and an orientation of your manifold. And you can get it by this expression here. So here, what I've written here is if you contract a vector field inside your freeform, you get a 2 form. And if you take another vector field you contract into your freeform, you get another 2 form. And then you can wedge them together. I'm going to get a 4 form, which I wedge again with my freeform. So I get something which is a 4 form, a 7 form, which is a top dimensional form. And this has to determine some volume form. And the coefficient of this term happens to be the metric. And if you check it with this pointwise model, you will find you get the standard Euclidean metric and the standard volume form at that point. Okay, this is just a matter of convention, and if you don't know about G2 geometry, now you've, learned it, let's say. So the basic example of a G2 structure is a product one. So you can just take any manifold that has an SU3 structure. So if a 6 manifold with an SU3 structure, you can take the product with an S1 factor, and you can define a G2 freeform by this expression here. Okay, sort of simplest example of a G2 structure, if you've never heard about it. Okay, so a G2 structure is said to be torsion-free if its freeform is currently constant with respect to the Lev-Shifter connection, so if it's parallel. And a classical theorem due to Fernandez and Gray says that this is in fact equivalent to asking that the freeform is closed and co-closed. Okay, so if it is parallel, clearly it has to be closed and co-closed. It's a converse statement is a non-trivial statement and requires a little bit of G2 representation theory. And just like in the SU3 case, there's a notion of intrinsic torsion. So the notion of intrinsic torsion is a failure of the holonomic group of the Lev-Shifter connection to reduce to G2. And this is given by some tensors, which I'm going to call tau. So it's going to be tau node, tau1, tau2, tau3. And just like in the SQ3 case, the subscript is going to tell you the type of tensor it is. So tau node is going to be a 0 form, so it's a function. Tau1 is a 1 form, tau2 is a 2 form, this is a 3 form. Okay, and the torsion forms are defined by taking the exterior differential of these two guys here. And what we'd like to do, we'd like to consider the same problem as in the almost Hermitian case, namely we would like to look for connections which have holonomy G2, but who has non-torsion free connection, but it's of skew-symmetric type and it is closed. Okay, that's the problem we would like to consider. So first thing first, we should ask, is there an example, when does there exist a G2 connection with skew-symmetric torsion? So the answer was again given by Fredrik and Ivanov in the same paper as before. They prove that yes, for there to exist a G2 connection with skew torsion, you need that some obstruction term vanishes. Namely, you need that the torsion form tau2 occurring in the differential of your 4 form, it has to be 0. So you should think of it, if you don't know anything about G2, you should think of it as asking, as some sort of analogous condition, as asking that the Ninhais tensor is skew symmetric. Okay, and again, in this case, if such a connection exists, it is also unique. So typically, you should not believe that for every H structure, there's typically an obstruction for there to exist a connection of skew symmetric type. So for instance, there's a result due to Ivanov back in 2004 that says that if your manifold has a spin 7 structure, then there's always a unique connection with skew symmetric torsion. So there's no obstruction in this case. So there's no condition on the torsion has to vanish or anything like this. So this typically, there's no uniform theory as far as I'm aware of. So for each different H structure, you're gonna have to check if there exists a connection with skew symmetric torsion or not. Okay, this is, as far as I know, this is not completely known in general. Okay, if there exists such a G2 connection, then you call this connection the characteristic connection, and you can compute its torsion in terms of the G2 torsion form, and it's given by this expression here. Just as in the SU3 case, there's a distinguished one form, which I'm going to call the G2 Lie form, which is this one form, which I call tau1 here. Okay, so this one form is the G2 Lie form, and it is somehow the analog of what we call as nu1 as a SU3 case. And a G2 structure would be called strong if the torsion is in fact closed. And this is naturally analog to the almost Bismuth-Hermitian-Einstein setup. So here's a second theorem that we have in the G2 case. So in the G2 case, we have the following statement. Suppose that the torsion form tau2 is 0. So that is the obstruction term to the existence of a skew symmetric of a G2 connection with skew symmetric torsion vanishes. If that's the case, and also that the torsion form tau node is in fact constant, then the following conditions here are equivalent. So that the G2 Lie form is parallel with respect to the characteristic connection, and the torsion form is co-closed, and the underlying G2 Lie form preserves the Lie form preserves the G2 structure. And this is again in perfect analogy to what we saw in the SU3 case. So there's a natural analog between the conditions that the Ninhais tensor is skew-symmetric and tau node is 0, and the conditions that tau node being constant and these tensors here being J invariant. Okay, so there's formal analogy between the two situations. And again, you can in both cases promote this condition to asking that the Ricci curvature of the characteristic connection in fact vanishes. So there's a perfect formal analogy between these two cases here. And in particular, if you ask that there exists a strong G2 structure with vanishing Ricci tensor, and the manifold is compact, then either the free form, as the torsion form, or the G2 free form would have to be harmonic. So in particular, this will have to define at least one element inside the third cohomology group. So typically, there's an obstruction for which 7 manifold can admit such a G2 structure with torsion. Okay, so this is all sort of topologically there's some obstruction. Okay, so let me tell you a little bit about how we prove this result. So the way we prove this result is by looking at something that Robert Bryant did in the sort of, he used it in the case of some G2 structures, but he didn't sort of do it in this strong case, and this is what we did. So what Robert had done is he had shown that whenever you have an H structure there's a certain whenever you have an A structure on a manifold, there's some differential invariant associated to the space. So in this case of G2, the space of first order invariant is what is known as the intrinsic torsion. So the intrinsic torsion has 4 terms. It has tau naught, tau 1, tau 2, tau 3, and this corresponds to each irreducible component that arise in the space of first order invariant of your G2 structure. Similarly, you can compute the space of second order invariance of your G2 structure, and this turns out to be given by this space here. So these are all different types of G2 modules. And all of them have a basis, so you can find a basis for each of these terms, and by finding a basis for this term, you can always express any second order quantities in terms of these basic elements. Okay, and this is what we did in the paper. We classified basically the basis for all these terms, and this allows you to generate a lot of formula for terms that you're interested in. So let me sort of just give you an example of, for instance, what Robert did. So what Robert did is he was interested in finding formulas for the scalar curvature and ridge curvature in the Riemannian case. And he had proven that the scalar curvature of the Riemannian metric can be expressed in terms of the torsion form by this formula here. Similarly, he had proven that the traceless ridge curvature, so here I'm identifying the symmetric tensors with the space of 4 forms of type 27. And you can have a very nice expression for the ridge curvature in this case. So you can use the same method as Robert did and apply it to the characteristic connection. And then you can again find a formula very neatly, like he did, almost immediately, that the scalar curvature is given by this formula and the ridge curvature is given by this term here. So in the characteristic case, this connection here has this ridge tensor has both a symmetric and skew symmetric part. And here this is just a traceless symmetric part. Similarly, you can apply the same method for all the other quantities that I've given to you before, the lead derivative terms, exterior differential of the torsion, so on and so forth. And the same method of proof works in the SU3 case by classifying first and second order invariance in the SU3 case. And this is how we prove this formula. Yes, tell me.
So the difference here is that you express this second order invariance in terms of the torsion in comparison with what Karagiannis, Trivedi, and Kanotis did.
Yeah.
In the paper. Okay.
Yeah. Yeah. So we classify this invariant, and then we expand all the quantities, and then it's just a matter of matching the quantities. Then you can prove that this quantity is equal to this, so you don't need any other global information somehow. It's just a local computation. Yeah. Yeah. Thanks. Okay. So as before, you get the same result as in the SU3 case. So because assuming that the Ricci of the characteristic connection vanishes, then the leaf form would have to be parallel. So again, there's a dichotomy. The leaf form either has constant size, has to have constant size, so it's either 0, or by normalizing, it has constant size 1. From the strong condition, you find out that the failure of the manifold being closed, so in particular torsion free in this case, is given by the leaf form and the norm square of tau naught. So an exact same thing we had noticed happened in the case of almost Bismuth-Hermitian-Einstein. In the Bismuth-Hermitian-Einstein case, where the G2 leaf form is replaced by the SU3 leaf form, and the norm square of the Ninhai tensor now gets replaced by the norm square of tau naught. Okay, and there's the same analogy as before. So again, if tau naught here was constant, so if this term here was 0, then your manifold would have to be torsion-free if and only if the leaf form is 0. But again, if your leaf form, if the tau naught was not constant, your leaf form in principle could be 0, and this will compensate for the fact that your G2 structure is not torsion-free. Okay, so the same dichotomy as in the SU3 case happens. And as before, the scalar curvature is always positive and vanishes if and only if it is torsion-free. So again, the same argument as before tells you that they do not occur in the case of solved manifolds. So let me tell you about some examples now. So the sort of simplest example you can have is if you take a hyperkähler manifold, or you can take the flat torus if you wanted, and an S3. So on S3, you define the left invariant one form E1, E2, E3. And you pair it naturally with the hyperkähler triple, omega 1, omega 2, omega 3 on your hyperkähler manifold, and you can define a G2 structure here by this formula. You can compute, in this case, that the leaf form is 0, but tau naught is not equal to 0, and the Ricci curvature of the characteristic connection vanishes, okay? And it is not typically flat unless your hyperkähler manifold is, in fact, flat itself. Second class of example you can do is you can just take the product of the previous example. So in the last case, I had two different type of SU3 structures on S3 cross S3. I had the Calabi-Ekman one, and I had also this other example which had skew-symmetric Nien-Heinz tensor, but it was not complex. Okay, so you can take the product with an S1, and this gives you a natural G2 structure on the total space, and you can compute that in both of these cases. The leaf form doesn't vanish, but tau naught in this case is 0. So in fact, these two different G2 structures are in fact not diffeomorphic to each other. Okay, you can check that. In fact, I think they are not even homotopic to each other. Okay. Okay, so again, you see that the dichotomy of before, that tau naught can be 0, or it could not be 0 as well, which was again this dichotomy that we had in the theorem. So it could vanish or it could not vanish as well. So again, both of the situation in fact does occur. It's not like one of them would always occur. So here's some things that I sort of probably some interesting questions that one can ask is, can one classify all possible strong G2 structures on S3 cross S3 times S1? So for instance, in this case here, we saw there's at least two different G2 structures which are strong. In fact, there was this work that I mentioned earlier in Viviana's question by Anna Fino, Lucia Martin Merchant, and Alberto Raffaello that says that if a manifold admits a strong G2 structure with torsion, then it has to be either S3 cross S3 cross S1, or it has to be S3 cross T4. This is the only homogeneous examples. But it doesn't say that in each cases the G2 structure has to be unique. And in fact, indeed, there exist two examples. In fact, there are more examples you can cook up by doing some rotations of complex free-zero form. Okay, so there are more examples, but they're not classified. So even in the spaces, there can be more than one example. Secondly, you can ask other examples where the manifold is strong, but the leaf form is not parallel. So it could be the case, can you have examples where the torsion is closed, but the Ricci of the characteristic connection is not 0? Can this in fact occur? Equivalently, you can ask the same question in the Bismuth-Hermitian-Einstein case, are there examples where the leaf form is not parallel? So these questions were the second question was open for a while, and the recent result by Apostolov that I mentioned before and collaborators is that yes, now it can happen. It can happen. The leaf form doesn't always have to be parallel. Okay, with respect to the Bismuth connection. And in the G2 connection, we already had an example with Anna. We only had a local example, so we do not have complete examples of this phenomenon at the moment. Okay. So I will just mention the examples we have. Let me check if I'm doing okay on time. Probably I'm all right. Okay, any question about what I said or anything that was not clear? No, okay, cool. So let me tell you about one way that we try to find example. So you would like to look for examples which satisfy dt is equal to 0, but Ricci doesn't necessarily have to be 0. So a classical example you can look at is the spinor bundle of S3. So the spinor bundle of S3 is topologically S3 cross S4. And this is you can make a cohomogeneity 1 ansatz on the space. So you can look at solutions which have SU2 cube symmetry. So this is one of the original example considered by Bryant and Salomon. So Bryant Salomon back in, I think, 89, they proved that on this space there exists a torsion-free G2 structure. It has a torsion-free G2 structure. So our natural ansatz was to try to look if on the same space you can have strong G2 structures with torsion, which are not torsion-free. That was the original idea that we had. So what we do is you start working on an open set. So you remove the 0 section where the OD sort of degenerate, and you impose on the open set. So you work on S3 cross S3 times the interval. You impose the conditions that tau2 is 0 and that the torsion is closed. This is a second order condition. So it gives you a system of second order ODs. And if you work a little bit, it turns out that you can actually integrate this equation to get a system of first order ODs, but now with a constant parameter C. So this gives you, in fact, a trichotomy in this case. So either C has to be 0, you can normalize it to be 0, 1, plus 1, or minus 1. If the constant C in this system of ODs is 0, then the equation truncates down, and instead, and this this equation here leads to the torsion-free condition, so T being 0, and so you recover the solutions found by Bryant and Salmon originally. So if C happens to be -1, then if you look at the system of ODEs, then it turns out there's one explicit solution, and the one explicit solution is obtained by looking at R cross S3 cross S3. So this is one of the original solutions that I told you about before. In that case, instead of R, you had an S1. So this is a universal cover of this guy here. So what happens is that here, we were trying to look at this S3 cross S3 on cross interval. Instead of degenerating at the 0 section, it never degenerates. You just get a cylinder. That's the second solution you find. And in the last case, when you try to look for solutions, there are explicit one. There's at least one explicit one, but there's a bunch of other solutions, and all of them are not complete. So all of the solutions, when you look at the OD, they all degenerate. So asymptotically, all of them are torsion-free. But as you move towards the 0 section, the OD degenerates, and so the solution is in fact never complete. It's always incomplete. So there's no new examples of strong G2 structures in these cases here. Okay, but this is with the SU3 cube symmetry. So in both of these cases, you can check that the torsion is, in all these cases, you can check that the torsion is closed and co-closed, but the underlying leaf form is not a killing vector field. We don't know if one can find complete solutions if we impose weaker symmetry group. So this sort of problem is a little bit related to what Lorenzo was talking about a few weeks ago in the Bismuth-Hermitian-Einstein case, in looking for sort of cohomogeneity 1 solutions. So this is like a G2 version of that problem. Okay. Okay. So the last thing we did in that regards is we were looking at the strong G2 structures with the vanishing of the Ricci curvature. So what happens if that happens? So we knew that the leaf form has to have constant size, so it's either 0 or 1. And it has to preserve the underlying G2 structure. But let's suppose for the time being that you're not in the first case. The leaf form is not 0. Then it has no constant norm, so you can do a dimensional reduction of your underlying G2 structure. So what you would like to do is you would like to sort of do the dimensional reduction, assuming this action is, the action is clearly free. So if you have the quotient, what sort of SU3 structure you get on the quotient? That is sort of, it's a very natural question to ask. And if you do that, you get the following Gibbons-Hawking type theorem. You prove that this is equivalent to asking that the quotient space is a 6-manifold with a half-flat SU3 structure, i.e. the leaf form of the SU3 structure is 0, and the real part of the complex free 0 form vanishes. But on the other hand, if you take the exterior differential of the imaginary part of the complex free 0 form, this is not 0. In fact, it's some positive number given by this guy here. Okay, and the curvature of this S1 bundle is in fact determined, it defines an integral cohomology class of type 1,1. Okay, so it's a Hermitian circle bundle. Okay, and in this case, on the quotient space, you can look at the derivative of your torsion, and in this case, it's not 0. In fact, it's related to Fe wedge Fe, the trace of Fe wedge Fe, and this is the so-called heterotic system. This is a so-called heterotic Bianchi identity. This is what you end up getting when you do the dimensional reduction. But again, you notice that this manifold can never be complex. Notice that the Ninhai tensor is always Q-symmetric, but never 0. But in fact, you can check that the bismuth Ricci form, in fact, it does vanish. Okay, so there are lots of examples of solutions to this Hull-Schrödinger system done by many people, and sort of recently it was sort of generalized in the work of Agnaldo and collaborators. And there's also work of Galdano in this direction here. Okay. Okay, so if you apply this construction to the examples on the Calabi-Ekman manifold, so on M7 with its on M7, which is S1 cross S3 cross S3, you do the dimensional reduction with respect to these two different G2 structures. In one of the cases, you end up getting S1 cross S2 cross S3. So in this case, somehow the S3, one of the S3 gets reduced to this S2 factor, whereas in the other case, it's the trivial bundle. The trivial bundle just goes away, and you just get S3 cross S3. So there's two different possible quotients you can get from this structure, which indeed shows you that they were not sort of diffeomorphic to each other. Okay, so now I'm going to move to the flow bit. Is there any sort of question, comments, maybe anything I said not too clear? Okay, probably not. Okay. So let me move to the last part of the talk, which is about sort of looking at geometric flows in this context. I'm doing okay on time, I guess. Okay. So we've noticed that it is a very hard problem to find these strong G2 structures with torsion. So we would like to find a geometric flow approach to this problem. So what are the known geometric flows that exist in the context of G2 geometry? Well, the most classical one is the so-called Laplacian flow, which was introduced by Robert Bryant. So in this case, what you do, you evolve your freeform by its Laplacian, and you run the flow, and hopefully eventually the critical point would have to be harmonic, and in particular this would imply, because it's already closed, it will have to be co-closed. Okay, so this is one of the methods of trying to construct torsion-free G2 structures. This method was sort of a replacement, so an analog to the Laplacian flow was suggested by the work of Karagiannis, Mackey, and Sui quite a bit afterwards, which suggested, well, instead of looking at the evolution of the freeform by Laplacian, you can just take the hot star of the whole thing and try to evolve the foreform instead by Laplacian. So this was a flow and proposed by Karagiannis and collaborators to try to find torsion-free G2 structures. And again, if the foreform is harmonic, then this condition here will, I mean, if this holds true and this is harmonic, then this implies that it will have to be closed as well. So again, it will be torsion-free. And the problem here with the Laplacian coflow is that it fails to have short-time existence. So while this flow has short-time existence, this one doesn't. This one does not have short-time existence. So in order to fix this problem, Sergei Grigoryan introduced a so-called modified Laplacian coflow. So what he did, he added some extra term to the previous flows that Spear and collaborators had considered, and now this flow has short-time existence. But the problem now is that this flow does not, the critical points of this flow are no longer torsion-free. So this was not a good method to find torsion-free G2 structures. So the idea was to, okay, so you cannot use this flow of Grigoryan to find torsion-free G2 structures, but maybe you could try to use this flow to find strong G2 structures with torsion. So this was a sort of guess that we had. So you can try to set up a variant of the modified Laplacian flow. So what you do is what you would like to do, you set up a geometric flow where you evolve your foreform by d of its torsion. Okay, so this is the perfect flow that you would like to run, and ideally you would run this flow, and in the limit you would find something which is strong, and it will give you a strong G2 structures with torsion. But the problem here is that this flow typically turns out not to have short-time existence, so you have to add some extra term to make it work. But surprisingly enough, this is the most general quasi-linear second-order flow of co-closed G2 structure that you can have. Okay. And this includes both the modified Laplacian coflow and the Laplacian flow, which occurs as special parameters. So yes, so our first result is that this flow always has short-time existence, provided this parameter lambda here lives in a certain range of values. So if lambda lives in this range of values, then this flow has short-time existence. Ideally, you would like to prove that lambda lambda can be taken to be 0. If lambda can be taken to be 0, I can set also C to be 0, then I would be able to kill off this whole bad term here, and then I would have a flow whose critical points would have to be the strong G2 structures. But unfortunately, that doesn't work. So it's better, so it extends previously known result, but it doesn't work. But there's a modified version of this flow that works, so I will not say anything about it, but Andres Moreno will give a talk in a few weeks about this. Okay, so this is just like a comment. Okay, so a second approach would be to try to copy something that does work in Hermitian geometry. So back in the days, Jeff Streets and Gang Tian introduced a so-called pluriclosed flow. So in the setup of pluriclosed flow, what you do is you evolve your Kähler form by the 1/1 part of its Bismuth-Ricci form. And they prove that this, in fact, preserves the SKT condition, and the critical point would have to be these Bismuth-Hermitian-Einstein guys. So, but the problem here is that you cannot quite copy this flow to the, let me say it this way. So when the two form evolve by this expression here, you can check that the underlying metric and the torsion form evolves in the following way. It evolves by the Ricci curvature, essentially by the generalized Ricci flow. So this is part of the generalized Ricci flow. up to some gauge fixing term. Okay, so this pluriclosed flow induces this gauge fixed solution to the generalized Ricci flow. So we can't generalize this to the G2 case, but this flow here definitely can be generalized to the G2 case. So this is a second attempt at trying to find some sort of geometric flow approach to finding strong G2 structures. So what we did with Anna, we said, well, let's consider a flow of G2 structures where the four form evolves by the following expression here. So again, you see as before, there's D of the torsion sitting there, and there's some extra term here. So let me ignore the extra term for the time being, but the nice thing here is that if the four form evolved by this expression here, then you can check that the metric will evolve by almost the generalized Ricci flow. It would be minus twice of the Ricci plus this quadratic term in the torsion. And then it has a gauge fixing term that comes from the Lie form, which is precisely what happened in the case of the pluriclosed flow. So this is why this flow here was set up. This flow induces precisely this condition here. But now there's a freedom because if I only want the metric to evolve by this way, there's a freedom of deforming the metric with it in isometric class. And this is given by a one form. And so there's a freedom of what possible flow I can pick. Notice that this flow works no matter what, because what I've done is I've taken the obstruction term tau2, which doesn't exist, and just shove it inside the problem, because I cannot typically prove that this condition here would be preserved by the flow. And what we did with Anna is we used the result due to Shubham and collaborators, so Shubham Dwivedi, Panagiotis Giannoutis, and Spiro Karagiannis had proven before that there's a whole family of G2 flows that have short-time existence under certain criterion. And what we use is we took their result and converted it to our setup, and we tried to find in which case as this flow that we sort of proposed would have short-time existence. And it turns out that as long as your one form, which you can sort of convert it into a two form by this G2 isomorphism here, is of the following form, if it is of this type, where this constant lambda1 and lambda2 lies in a certain nice range of values, then this flow will always have short-time existence. Okay, this flow will always have short-time existence for this constant here. And the nice thing is that we do not typically need the obstruction to be zero for this. This flow will always work whether the obstruction term vanishes or not. And in fact, you can prove that if the obstruction term vanishes, then there's very few possibilities for the choice of this one form here. This isometric term has to be quite limited if that torsion form here is zero. So if we could choose this isometric one form, this one form that deforms the metric isometrically, so that the torsion form tau2 is always zero, can we find such a flow? Can we choose F1 to satisfy this property? If yes, can we also assume that, can we choose this one form so that the free form evolves by sublation plus a Lie derivative type term? If we could choose this to hold true, then we would have obtained an analog of the pluriclosed flow, because the pluriclosed flow induces this gauge fixed version of the generalized Ricci flow, and this is what we would like to have in the G2 case. But the problem here is in the G2 case is that in general, in this case, the complex structure is always the same. So the Nin-Heiss tensor is always zero. So this is a condition you get for free. In the G2 case, you don't quite get this condition for free. So you have to impose that tau2 is zero somehow. But this is not, when you evolve the G2 structure, tau2 evolves as well. So you cannot quite control this. So if you were able to control this, then you would be able to find a flow that would be somehow a good analog of the pluriclosed flow. But we have not been able to do this. But it is tempting to believe that because of the analogy in the previous theorems, that the Nin-Heiss tensor is somehow related to this torsion tau naught, that if you impose that tau naught is zero, then somehow the manifold would behave a little bit like in the complex situation, and you might be able to make this analog version of this G2 version of the pluriclosed flow work. But we don't know if that can happen. Okay, so that's all I wanted to say in this talk.
Thanks, Udolf, for the very nice talk. Are there more questions? So yeah, well, I guess maybe I just ask. So I guess you tried to also cook it up in a way to solve for this PDE for T for the torsion.
Yes, yes. So yeah, so we would try to. I mean, ideally, you would try to evolve it in this way here, but this turns out not to work out very well. So you have to add in some extra term. I mean, so this is what you would like, but to have short-time existence, you have to add some extra term. But then you do not know that tau2, if initially it is 0, that it is preserved, right? So this is the problem. We don't know that. So what we say to do is, well, okay, we cannot control how tau2 evolves, so might as well just throw it into the flow as well. So we just say, let's throw in the obstruction term as well and just evolve it just as a G2 structure. Okay, so not preserving the interoperability condition whatsoever.
Right.
So ideally, we would hope that if initially it was interoperable, so if initially tau2 was 0, then this flow would just preserve that condition. Just like sort of in the complex case, if the manifold was complex, then it will stay complex. So this is what one would hope to have. But the problem is that once you start to evolve, once you start to compute this, life gets very hard because the computation gets quite evolved, yes. Also because the freedom. Yeah.
Right.
Yeah. But yeah, I don't know. But maybe, I mean, can one even actually make this pre-closed flow work in the case where the inheritance is just Q? Can we make the flow work in this case? That would be somehow the natural analog of an almost Hermitian version of this. Yeah. But even this, I don't know. Maybe, yeah. If that can be made.
Yeah, I think that's a very interesting question. I think that would be very nice. That could be done. Yeah. Okay, yeah. Are there others? Okay, if not, let's thank Udolf again for the very nice talk.
Thanks.